I'm gonna make a couple of remarks. Um, a term that we have been using and that is really important is homotopy type, right? Homotopy type. Homotopy type. Okay. So the homotopy type. So one of the things that most people might not know is that, well, I don't know, most people, well, some of you don't know, is if you don't know what the homotopy type is exactly, you can always think of shrinking. Like this is called retraction. I don't know, deformation retraction of a space. So, for example, if you have this surface here, you can retract the surface, deformation retract this surface into this shape, right? So you can squeeze it down to this shape, but also you can squeeze it down in this shape or this other shape, like this. You can squish it down any of these shapes. But these two shapes here also are said to be homotopically equivalent. So this one is homotopically equivalent to this one because can be squished down to this one. And also these two are homotopically equivalent. And because we want an equivalence, these two are also equivalent. So you can always think that homotopically equivalent means that there is a third space. You have two spaces that are homotopically equivalent mean that there is a third space that deformation retracts into the other two. Yeah, this is a way of understanding homotopically, just having the same homotopy type. If you don't see it, you just try to look for a third space that retract to both of them. Just as a simple way of looking at the homotopy type. So the other thing that I want to talk about was coefficients, homology with coefficients. With coefficients. So especially we build homology with coefficients in the we integer coefficients. So we talk about Cn of k as the free abelian group generated by the n simplices. But instead of that, there is no reason for us to talk just about the abelian group generated by those, but we can talk about other things. So instead of consider all the possible sums with the z coefficients, we can talk. We can rather work with Cn of k, the vector space generated by the n simplexes. So in this case, if this is simpler for you, the vector space can be, we can have the coefficients of any on a field. But if you are not familiar with fields or you just feel uncomfortable working with fields, you can always think about, I don't know, this is Rm with m, the number of simplices. Or the one that people usually they use the most in algorithms in computer, in computational computer. Well, it's we just saying stupid things. Okay, so is working with C2. C2 is the one that people use the most because, well, it's simpler, it has less elements, and the arithmetics are pretty easy to do. For computers, it's pretty easy. So yeah, well, this one is the better. And so the way when you work with this when you work in this case, the homology is usually written as Hn k with coefficients in C2, right? And so this is and in this case, what you have here is a vector space. vector space. Vector space. You prefer, you can work with R or the rationals, and with any field, it becomes a vector space, and everything is simpler for computations. Remember that we were working with Cn of k, n plus 1, Cn k, and Vn Cn minus 1. So if you want to compute the homology in this case is the kernel of En divided by the image of Dn plus 1. So in this case, if we have the before we have to compute the Smith normal form of this transformation, but when we are working with vector spaces, so and we know that the image of these vectors, this kernel of Gn is a vector space, and this one is also a vector space. The only thing that we need to compute here are the dimensions of the spaces. So what is the dimension of this space divided by the dimension of this space? That will mean that the total dimension is going to be just the subtraction of dimensions. So at the end, it's just going to be V2 to R minus S, with R is the dimension of kernel of Dn, and S is going to be the dimension of image of Dn plus 1. So computationally is much easier this way than the case when we have C coefficients. So we're gonna so most of what I'm gonna do next, we're gonna think that we're gonna use any of these kind of coefficients, field coefficients. So I'm gonna name these coefficients K or R. K. So K can be C2 or can be R or can be the rationals, but then this thing is gonna be a vector space. And so things are gonna be much simpler. So once that we have that, so here's another thing that we need are the induced maps. The induced maps, this is something that we didn't say much about. But in case of sequential complexes, if you want to use as an induced map, you want to induce a morphism between the homologies. You need a function that goes from one simplicial complex to the other, and you need that condition on the simplicial complex. So that means that you have vertexes. So the one phase need to be mapped to another phase, but in this case, the vertices need to be mapped to vertices, and the images in the vertices span another simplex. So it's on L. So as an example, imagine that you have something like this. It is a triangle, and you can map it. Let's see something more complicated. Something like this, and you can map it to something like something like this. Simply. So you can map this vertex. So the only thing that you need to do to define a simplicial map is to define what happened with each vertex. So you have this vertex, where it should be mapped. So this is in the vertex, P of B0. What happened with this vertex? And this is going to be F in V1. What happened with this vertex? Well, that vertex is going to be mapped here. V2. What is going to happen with this vertex? Well, I can map it over here as well. Once that I decide where all the vertices were mapped, the only thing that I need to check is that simplexes are mapped to simplexes. For example, this simplex is mapped to this simplex. This simplex is mapped to a point, which is also a simplex. This simplex is mapped to a segment, which is also a simplex. one thing that, and also I can just have this space, for example, and this also works perfectly. The only problem is the only kind of function that it doesn't work as a simplicial map. An example where things don't work is, for example, if I have something like a simplicial complex like this, 4 edges, V0, V1, V2, V3, and okay, and I want to map it. Well, if I know something more complex, well, the same simplex, but I want to map it over here. And I want to map it over here. Yeah, but yeah, and I decide to map F0 here, but I made the wrong decision to map F1, V1 to F1. And V2 here, I'm gonna better go like this to create a counterexample, and this is V3. This is not right. The problem here is exactly V0 and V1. This simplex is being mapped to this point, right? Which is no problem. This edge V0, V3 is mapped to V0, V3, which is there's no problem. V2 and V3 also are mapped to different points, so they're mapped to this edge. They'll also with V1 and V2 are mapped to this edge. There is no problem at that point. But what happened with this triangle? So V1 is mapped here, V2 is mapped here, and V3 is mapped here. So this triangle, the entire triangle is mapped to an spanning triangle here, but that triangle doesn't exist here. So then this is not a simplicial. This function doesn't induce a simplicial map. So there are some functions that induce a simplicial map. There are others that don't. So if we assume that we have a function that induces a simplicial map, then that function defines a new function between the homologies. Because simplicial complexes here are being mapped to simplicial complexes here. So the n-dimensional simplex is being mapped to another n-dimensional simplex here, and can be computed, and you can compute the homology. So that kind of function define induce a map between the homologies of simplicial complexes. And here is an example, very basic example. I have here a triangle, and then that triangle is contained here. Inclusions are the most simple kind of simplicial maps. So here in the inclusion, and here in the inclusion of this thing to the other one. And here we have the homologies of those things. So the first homology group of a triangle, well, remember, when I draw a triangle here, I mean just the edges. There is nothing is filling in the triangle. So it's a loop, it's a hole. So the first homology group is E. This one is two triangles. So that means there are two holes. So the first homology group here is C2. And in this other side, we have the same thing again. We're copying a triangle here, and copying a hole with a triangle, and then that gives us only one hole, and that's in the first homology group. So and then these are the induced maps. The induced maps. So the first homology group of this thing maps this triangle onto this triangle, right? So that means that this cycle is being mapped to this cycle. Right? So the generator of this group is being mapped to the first generator of this group. The second generator of the other group is not being touched at all. So that's why the transformation is making like 1, 0. So it's just taking any integer is being mapped to n times the first entry, 0 times the second entry. And this other map, take the two holes, map those two holes. One hole is mapped into this hole that is still there, and the other hole is being mapped to the boundary of the triangle, which make it trivial. implicit boundary something is trivial in the homology. So this map is mapping the two generators. The first generator is kept as generator on the next group, but the second generator is being mapped to 0. So the induced map defined by the induced map by the inclusions, not necessarily meant inclusion maps, right? On the homology. So in the first homology group, this is an inclusion, but this one is a projection. Yes. So this one is just including Z inside C2, but this one is killing one Z. Right? Yeah. So not because it's an inclusion will meant that you have an inclusion of groups. And this is important to understand persistent homology, right? What kind of things, what is going on in this process is sometimes generators get live for a period of time or die in a certain moment. Yeah. Complete. And so that's that. The thing about persistent homology. What we're gonna do is just work with this kind of sequences of simplexes. So check of R is just a simplex. And you can construct a bigger simplex, a bigger simplicial complex when you increase the radius of the circles. That is the check of S. Right. So as an example, if you take just 3 points, for example, 3 points, imagine just these 3 points. This one and one here, a distance. The distance between these two is 1. The distance between these two is 2. And so if you start with a very small circles, if this is the radius, R1. If you start with radius, I don't know, check of radius 1/3, you will get this simplex, just 3 points, isolated 3 points. But this is contained in check of 1.5. 1.5. What is going to happen with check of, I don't know, 0.8. I don't know. So check of 0.8. What happens when you take balls of radius 0.8? These two balls are going to intersect, but this one don't. And so you will have this influential complex. And when but this one is contained here because the points are still there. And then when you construct check of radius 1.2, you will get this thing. It's a bigger complex. And then when you have check of 2, you will get this thing entirely. That's I think you will get the entire thing, right? You will have the triple intersection because you will have intersection between these two, and this one is also gonna intersect here, no? So you will have something like that. And so, this is called a filtration of complexes. So in general, persistent homology is going to work for filtration of a simplicial complex. So the check complex is basically a filtration of a simplicial complex, and the Viatori strip is also a filtration of a simplicial complex, and also the alpha complexes are a filtration of simplicial complex. So you have, when you increase the radius, you will increase the size of the simplicial complex, one containing on the into the next one. So once that you have a filtration, usually we are going to write like this. K of R containing of K of S R lower or equal than S. And then associated to it, we are going to compute the homology and induce maps. Homology. And you have an inducing between the homologies of the spaces. So we compute the homology, and we, for every filtration, when we have filtration, we compute the homologies and we get those things. But this is a filtration of vector spaces. So this thing that we got here, this thing, when you took a filtration and you took these maps, this you have a, this is a vector space. When you fix the R and you fix the N, you get a vector space. Well, if you put coefficients on K in a field, in Z2 and R, we're going to think of this as a vector space. We have a vector space, we have a vector space, and we have maps between the vector spaces. But these maps exist only if we have R lower than or equal than S, right? This thing that we have here is what is known as posed representation. Posed representations. Posed representations. Posed means partial ordered sets, right? And, well, in this case, we are using a totally ordered set. The real numbers we are using now in real numbers we are equal than 0, and so we have a much bigger example. Well, a very large example of an ordered set. So, but in general, if you have a posed set, and a representation means just mapping the elements of the ordered set. You use the elements of the ordered set as subindexes of a family of vector spaces. So this means the category of vector spaces of their field K. So for every index in T, you construct a vector space V sub R. In this case, we are constructing, this is our V sub R. So it only depends on the R. The N, we can leave the N fixed. We can change it at any moment. But we got vector spaces associated with the posed. And so this vector, but also in the poseds, and when I is lower or equal than J, you have also maps Fij from Vi to Vj, such that we satisfy a condition of commutativity. So the thing is that between every 2 points, one that is lower than the other, between vector spaces, you have a function. This function not necessarily is injective or superjective or onto or nothing like that. It's just a function, like induced. In our case, is one of the functions induced by the inclusion, but not necessarily an inclusion, right? Or an injective. So once that we have a map, this means a map between vector spaces, but the condition about being induced by inclusions like this translates into the fact that if we have K lower or equal than J, lower or equal than K, we have all these commutativity of diagrams. If Fij, Fik, Fij, Fjk, and so we have this function because I is lower or equal than J. We have this function because J is lower or equal than K, and we have this other function. But we're going to need this diagram to commute. We need this diagram to commute, which means Fij composed with Fjk is equal to Fik. So that's the condition that we need. So basically, even basically the composition of two functions with one in the middle is going to give you the other one. It's a very reasonable thing to happen, and that happens here also. In this context, it also happens. So this thing is a posed representation. It's a posed representation. Well, one cool thing about posed representations is that it says there the family of representations of a posed, ref T, is an abelian category. Is an abelian category. Meaning that you can do basically all that you can do in linear algebra. If you have two representations, you can add them up. You can talk about functions between two representations, and you can add them up as well. You can add two representations together, and you can add. You can do a lot of things like taking kernels and stuff like that. Okay? Well, so one of the important parts is the important parts here is that you can talk about adding representation. So you can talk about you have a representation. A representation basically is just a sequence, an ordered sequence, because it's a posed, it's an order thing that has order. You have, in the case of homology, posed representations means just for every number in the positive real numbers, you have a vector space, and then you have another vector space, and you have a function between the vector space for every pair, right? But you can have another representation of the real numbers W and WS. For every real number, you have one vector space, another vector space for this real number, for this real number, for this real number. You can have vectors. These are two separate representations of the real numbers with vector space, and it has all the conditions here. These are FRS, and you have GRS. And you can add them up. You can add them up, these two representations, and create a new representation where you have VR plus WR. Yeah, and on S you have VS plus WS. And the function that you will have here is just the one that you had before, added with the function that the other one. The former. So that way you can add up representations and create new representations. This is a very interesting thing, and this is a theorem from Crowlers and Lowes, and I think Lowes, that if you have T as a set of the reals, in every point-wise finite dimensional representation of T, if you have any representation of T, even a subset of the reals, is a sum of intervals, and that sum is unique. What is an interval? An interval in the reals is just an interval in the reals is just a representation that you can write like this. Okay? It's a representation when you have for every it's a representation where the vector space associated with this representation is just your seal when R is in AV intersection T and zero otherwise. So when R is between those when R is between this interval, in the interval you got the field, the one-dimensional vector space, and between, if R lower than equal to S and S in the interval, then you have the identity map. FRS is just the identity map. The identity map on K. It's just the function that goes from K to K with identity. This is VR, and this is VS. And in the other cases, it's the zero map. When one of these is in the other cases, one of these is going to be zero, so it's going to be the zero map. Anyways, so this is an interval. So what this says is that no, it doesn't matter what kind of positive representation you have, but it has some conditions of point-wise finite dimensional. That means that we are representing every index with a finite dimensional vector space. We are not working with infinite dimensional vector spaces here, just finite dimensional vector spaces on each point. We have a finite dimensional vector space on each point. So if we are in that case, then we can decompose. So if V is any representation, every representation, then V can be written as the sum of intervals. Every family of indexes. So you can decompose it that way. Here I'm just skipping some possibilities, because when they meant interval, that they not necessarily meant closed intervals. It can also be, you can also talk about AV, semi-open or some semi-closed intervals, or open intervals. They can length every close in one side and open in the other one. Yeah, that's things like that. Yeah. So these are representations, right? So at the end, so you can think of that like in the interval, the interval that you refer to, you put in A, just a one-dimensional vector space, and between those, you're putting the identity map. And outside of here, you just put in the zero vector space. So so any representation that you have of vector spaces can be decomposed on the sum of these things. That's the theorem. So and this is a very interesting way. Well, so the fact here is that I need to switch probably what part of the interval is open, which part of the interval is closed. But so in order to avoid those complications, they write it like this, right? AI, VI, plus minus, plus minus, plus minus. Something like that. Yeah, that's the way that you like. So the math plus minus, or the plus or minus thingy that they put on that thing is just another way of denoting the open or closed intervals, for example. So then, so given a vector space, given a representation, we define the diagram of that representation as the pairs of B's and D's. The pairs of B's and D's. So, and that is a persistent diagram. Yeah. Do it. Yeah. Yeah, just point-wise. Yeah, point-wise finite dimensional. So then probably you can just increase the dimension when you go to the infinity, and then you will need to add more and more summands, more representations here. Yeah. You need to add more and more intervals. Yeah, that's good. Yeah, probably. Yeah, the most classic sense. Considering and it's not the fact that what you normally have in a great spot, they name that, but that's so you have that knowledge of it. So my thing, but how can like that is not great. That's not that. I'm it. No, I don't. don't remember. I don't remember the proof. I don't really look through it. Probably we didn't went through it in the time that we checked about this theorem. But yeah, no, I sorry, I cannot give you more insight about the proof. Yep. But yeah, I haven't checked the proof really. But yeah, but it's an interesting theorem, right? Interesting theorem. The decomposition of this thing.
So I am not sure if we can define the persistence diagram with this generality, because the way we are talking about T, so this subset of the real line, it could be, for example, the rationals, right?
It
So
can be the rational.
then it's not clear that intervals have endpoints. For example, there is an interval by the rationals less than square root of 2 and so on.
Yeah.
So maybe not every choice of T would yield a persistence diagram, right?
Well, yeah, A and B can be the square root of 2. Yeah.
Maybe not. Okay, we go outside of T and
We go outside of T to create the decomposition. Yeah.
okay.
It can go outside of T.
Thank you. Thank you. Maybe not.
Okay. And so
Maybe not.
So in our case, so we're gonna take any filtration, just given by any of these three cases or whatever or any other filtration that you like. We call it K sub R. We compute the homology, which gives us vector spaces, and this is a representation of the real numbers or the positive real numbers. This is a representation of that poset, and then we can associate to that filtration a diagram. That's the persistent diagram of KR. And another thing is that these filtrations can also be understood as preimages of functions from X to R.
Maybe not.
Yeah, that's another subject. Let's see. Let's look at an example of how to construct a persistent diagram. And this is an example where we create a filtration, we create a filtration of these are not simplexes, but these are in these examples we're looking at our topological spaces. It's a filtration of topological spaces, and we can also construct the homology of those things. So here, consider that curve. This is the curve is X. This is the curve. This is the curve that you're looking there. Is this set? Yeah, and
maybe not.
And we are thinking about this function that maps points here to what? This is in the XY coordinates, right? And so we are thinking about the filtration X sub A as the preimage of minus infinite,
maybe not
A. Yeah. So this is a filtration of spaces. So this is, for example, X sub B is the preimage of F minus 1 infinite to B, which looks like this. But it's just this arc at the bottom right here. Right. Let me see if I can point it with this thing. Is this arc right here? Yes, it are. Well, no. Is that actually? It does not include the ends, right? It's just that arc. And I know then if you look at it, so we have XA, which is just nothing, which is just empty. Okay? Then, but for any value R between between A and B, XR is just a piece of that arc. A piece of the arc. Is a piece is a small piece of this arc, right? But how many connected components does it have? XR. How many connected components? One is just one connected component. So A0 is gonna be R. Okay? So it's just one connected component, or just the field. Well, here I call it R, right? The field. Okay, K. It's K. Mm-hmm. K is the field. Very good. So it's just one dimensional for every R between A and B. And after B, how many components do we have for R between B and C? What is H0 of R? Yeah, in that case we have all of this and this, right? Two pieces. They never touch each other because even in the value C, they don't touch each other, because that point at the level C does not belong to the pieces. So we have this thing is K squared. K squared. So and how things are being mapped between these two things. So basically we have something like this. So we have A, B, C, D, and E. And up to A, this is 0. Then on all this interval we have K. All of this on these points we have K, and between B and C we have K squared. What happened with things between C and D? K again, and between D and E, yeah, K squared again. And from E and beyond, it's still K, yeah, because it's just one big component. Between D and E, we have, if we don't go all the way to E, we're going to have this and this. There's two components between D and E. So, and how the maps are going to go for these things. So, from K to K squared, what kind of map do you have? So between two of them, between two in the middle, you will have the identity always, right? Because it's basically the same components, it's just a little bit longer. So just have the identity map between things in the middle of these points. But what happened with something here? What is going to happen? So you have for the first one, for example, between A and B, you have something like here. And for C and D, you have something like this. So you have the orange one maps into the green one, right? So you have one generator in the orange one being mapped into the green one. Okay? So that means that generator here is just being mapped to alpha 0, right? This is kind of the map that you get here. The second part, the second coordinate represents the other new component, the one on the left. If you want to keep track of the right component, left component, we can switch changing bases, but we're going to keep it like that so far. And what happens when you have between these two, K squared to CD? So you have two coordinates, right? Alpha and beta. How is being mapped here? So it is K is the so the green one is mapped to the first component of the yellow one. Yes. They become the same, right? So how are they being mapped? Huh? Like something like alpha plus beta? Something? No. Do you think that makes? Yeah, the matrix. What kind of matrix? One matrix. What? One. Yeah, one. Exactly. Which is these transformations. It's him. So the two coordinates have been added in creating the new alert. So this is the 1, 1. In this one, if you want to put it as a matrix, is 1, 0. And then A square. What is the other map? Time's up. No, time's up. well. So we need to finish this soon enough. And so the thing is that again, we're gonna get something like 1, 0. Yeah. So we're gonna get another component, and then we have this one also, which is gonna be 1, 1. Then what? But the thing is, you need to change the bases in order to these ones become 1, 0, 1, 0, or and this thing can be decomposed. The sum of these things plus. So you have K surviving all the time. This is one of the intervals. The other interval is going to be the one that goes from here to here, which is K 0. And the other one is another K that is around this interval. So in this interval you have a K, in this interval you have another K, and so that's the sum of these two things. So you have a thing that lives start living on B and ends up dying on C. You have another component that starts at D and dies at E. So you have this decompose at this interval of all cases at K here and plus K here. So 3 intervals. So this is this long interval with just 1K, this small interval with just 1K, and this other interval with just 1K. That's the addition. And that is represented on that diagram. That one starts at A and never dies. The other one starts at B and dies at C. So that's represented by the point B, comma C. And the other one is the D, comma E, which is the other point. So 3 points representing the diagram. Well, and just to finish, there is a bunch of things that happen with persistent homology. And for example, this is a theorem of stability that if you perturb a little bit your space, that persistent diagram is going to look very similar. For example, the red curve give us the 2 dots that are in the diagram, but the blue curve give us all the blue points down here, and also very close points to the red ones. The red point that has P, comma S are basically 2 points that lands in the same space. It's a multi-set. And this is the persistent homology of this set of points. This set of points has, I took this from a book that is called Persistent Homology Through Quiver Theory. And this is a persistent diagram. When you look at this data set, what is the form of this data? What is the shape of this data? This is a bunch of Bs, 11 Bs, or is just one big A? Probably it's just one big A, right? Or is just like 200 points or something like that. So what is the shape? So when this is depends on the scale that you look at the data. If you look very closely, just bunch of points, right? If you move further away, you look like several B's, no? B's. If you move even further away, it looks like an A. And that is computed in the persistent diagram. This is a version of the persistent diagram where the lines represent all these intervals, additions of the composition of the persistent homology, and these intervals represents the number of holes. For example, from 3 to 4, you find 11 holes and other 11 holes, 22 holes. Those holes are the holes in the piece. Right? So you're kind of detecting but also at the same time you find 11 components in the zero homology. So in this interval, you notice that at this scale, you have 11 components having 11 connected components having 22 holes, which means each component having 2 holes, more or less, right? So you have 11 components having 2 holes. So that's why you are detecting there. And if you increase the scale, at this point, you notice that this is just one big component with one hole, which is the A that you're looking at. So the persistent homology allows you to understand your data in this kind of manner, like in different scales. That's what the picture of persistent homology is giving you. Yeah. Well, that's all for me. Thank you very much.